Okay, so last time we were talking about intersection stuff, and today we will be finishing up the discussion on that. So remember last time we saw like you have a little torus and you want to take the intersection of two things like this. So we took two sort of differential forms associated to each of the tori. So, each of the circles. So if this one is S1 and this one's S2, we took some form phi S1, which is this form that's sort of it's of complementary dimension and it's in the direction perpendicular to the submanifold that you have. And it's sort of like a bump form in the perpendicular direction, just like we saw with Myopia torus. And with S2, we have a similar form over here. And we saw that we can compute intersections in three different ways. So one way is that we can take the integral of phi S1 over S2. Another way we can do this is take the integral over S1 of phi S2. Or a third way that we can do this is, or I guess first, remember that the reason that this works is, for example, if we restrict phi S1 to the S2 picture, what we'll have is something which is 0, 0, 0, 0, 0 until it hits an intersection point and goes to 1. And so with this picture, another thing that we can do is we can look at the product of these two. So phi S1 wedge, phi S2. And what happens here is this is a bump form sort of in this direction. This is a bump form in this perpendicular direction. So when you take their product, what happens is you get a bump form which, well, one of them is like 0 outside of this circle. One of them is 0 outside of this circle. So you get something which is just concentrated at their intersection as sort of a two-way bump function, which will look like bump times dx dy locally. So a third way that you can compute this integral is the integral over your entire manifold of phi S1 times, or wedge, phi S2. So I guess first, just to sort of give another example, maybe let's say we're working in sort of a three-dimensional space, so R3, even though in R3 the case is kind of boring. So if you have like a plane, then the form, this is by the way called the Thom class of the submanifold. So the Thom class to this plane, for example, is going to be perpendicular in this direction. And if you have a line, the Thom class would sort of be radially concentrated and sort of a bump form sort of radially outwards from this. So if the coordinates were like x, y, z, then the Thom class over here would look like some bump form times dz, because it's only picking up the perpendicular z direction. And over here, the picture would look like some bump, sort of a, but this is a bump form of the z coordinate. And this is going to be a bump form of the radial coordinate r, so it dies off as the radius gets large, or as x and y both get large. And this will be times dx dy. Good questions? Okay. Yeah.
And that's because it's the complementary dimension or whatever. This one was 2, so that's why.
Right. So it's always going to be in the perpendicular direction. So in this case, because you have a plane, you have something in the one-dimensional perpendicular direction. In this case, because it's a line, you have something in the two-dimensional perpendicular directions here. Yeah, so that begs the good question as to like, why do we want it to be something in the perpendicular direction? This would have worked just as well, for example, if we associated a two-dimensional class to this, which is like here, and a one-dimensional class to this, and still the intersection would, if you take like the wedge product, for example, then you would still get the correct intersection formula. So this formula would still work. But one thing is that these formulas no longer work because, for example, if you took this planar 2 form, something that looks like dx dy, and you integrate it across this perpendicular line, then because the line is pointing in the z direction, this will evaluate to 0, and so the integral is equal to 0, which is not what you want. Another reason to have something in the perpendicular direction is that here you can take into account intersections, not just like where, if the codimensions add to the total dimension of the space, then you'll get a finite intersection. But what this allows you to do is also take intersections where the codimensions don't add up to the full dimension of the space. In other words, you don't have like just points of intersection. So one example is like, say, again, we're working in R3, and say you have two different planes over here. So these two planes will intersect in this line. And how can you see this using the differential forms approach? Well, what you can do is you can take the, how should I draw this? Let's see. Let's say you take your two planes, and let's make one of these differential forms purple pointing in this perpendicular direction, and one of these differential forms green pointing in this direction. So you'll see that the only, if you take the wedge product of these two guys, the only place where they have non-zero support is over the intersection of these two lines. And over the intersection, you're going to have something which is like dx times something which is like dy, and it'll have a bump form. So it'll look like the Thom class of this line over here. Does that make sense?
So you're saying that rather than getting a number representing the intersection, you're going to get a form, which is the Thom class of the intersection?
Right. So I'm saying that this sort of generalizes intersections from being points to just general submanifolds. So sort
Where
of,
you never integrate. You never integrate it.
you don't have to integrate it. Yeah. Like, okay, so what happens is,
But what
like,
happened if you did
say that you have something like this, right? So if you take the product of the Thom class, you get something concentrated over here, something concentrated over here. So if you take phi1 wedge phi2,
Is that a circle line?
yeah, so sorry, maybe I should color these things differently. So these are your two submanifolds, and then your form is going to be concentrated over here and over here, and this is your form. Now, if you integrate, let's call this form, say omega.
And that's
Now,
a two form, right?
Yes, this is a two form, if we're working in R2. So if we integrate omega over R2, which makes sense, again, because this is a two form, and that's because, for example, you have a one form perpendicular to this guy and a one form perpendicular to this guy, so when you multiply them to get a two form, and so if you take the integral of this, you'll get 2. So the integral of this differential form gives you a number, which is the number of points of intersection that you have, but before you integrate, you get a differential form. And this differential form is a bit more powerful because in this case up here, you have one line of intersection, right? But for example, say you had something like a sphere intersect a plane. Now if you take the product of the Thom classes, what you'll get is some sort of a bump form which is concentrated along this intersection equator and is in the directions perpendicular to the equator. So it'll sort of be concentrated, the d values will be in this direction and in this direction, but not tangent to the circle.
So it's a two form.
Yeah, so it's a two form. And so again, you see like this is codimension 1. This is also codimension 1. So the intersection is going to be codimension 2. And this is nice because the intersection of two things, the codimensions add up, and that sort of corresponds to taking the product of these classes, which have codimension. So maybe we can discuss why.
Can I ask a quick question?
Yeah.
So you're just saying your Thom classes are these bump functions?
Yes.
But like a priori before they were intersected, it's not a bump at that specific plane of intersection, right? So wouldn't it start out as just like a uniform thing over the entire submanifold? Like our phi's, why are they bumps at the point of intersection, or are they not?
I think he didn't say they were, not until you like wedged them to the original.
So for example, say you take a You always start with the, so the thing that we're trying to construct is, or the thing that we will construct in a moment, is say you have a submanifold, right? And this has some perpendicular directions. So you want some form. So this is a k-dimensional submanifold. And so you want to construct a form such that if we look at a plane, for example, if we zoom in on this plane, which is perpendicular, so this is n minus k dimensional, where our total dimension is n, then the form is going to look like something which is bumpy near 0 and goes to 0 outside. So it is concentrated near the manifold itself.
Oh, when
So
you say bump, it's
bumpy
uniform
everywhere.
over the submanifold, but bumpy in the
In the perpendicular directions.
Oh, okay.
Yeah, yeah.
Right, I forgot it is bumpy.
Yeah. So it's sort of a, yeah, you should think of it as like sort of a little, we'll see when you construct it. I don't know if you've seen the concept of a tubular neighborhood before, but it's like sort of thicken your submanifold a little bit, and it's going to be concentrated over there, and it's going to be a bump in the direction perpendicular to this. So maybe a nice thing to see is like, say you have some total dimension n, and say you have a codimension k and l thing. So say that this is like n1 and this is n2. So let's see what the dimension of n1 intersect n2 is going to be. So what happens in nice cases? Well, when they intersect, this is sort of a linear algebra problem, where here you have something of dimension n minus k, and here you have something of dimension n minus l. And there's this condition of transversality, which I guess I won't go over too carefully. But the idea is basically like, if you look on a small scale, it'll act as like the two tangent planes are as separated as possible. And what happens in that case is, for example, if we have a two-dimensional thing, if n equals 3 and k and l are equal to 2, then you have a two-dimensional thing and two-dimensional thing. So the way that you can compute the dimension of the intersection is by taking the sum of the dimensions and then subtracting off the total dimension of your space, if that makes sense. I guess there is something to be shown there. But you can show that using like some rank nullity or something, that this should be the dimension of the intersection, which is equal to n minus k plus l. So we see that dimensions are kind of messy to work with because you start with something of dimension n minus k, and you start with something of dimension n minus l, and you end up with n minus k plus l. But if you look at the codimensions, it's nice. And so these Thom classes give you something of codimension, that amount. And so it's nice because you can take products of these Thom classes and they correspond to intersections. So
sorry, can I ask? So I think I sort of get it more now. But when you took the integral of the intersection, why is it that you could guarantee that the integral of the intersection would be like precisely 2, as opposed to just like a sum of 2 contributions from the intersections of the bumps?
Yeah, so one other important factor that you want to take into account for this is up here, you want this total integral in the normal direction is equal to 1. And so it's kind of like a Fubini sort of a thing, where it's like you have something in these directions which integrate to 1, and something in these directions which integrate to 1. So you're just taking the product of two things, right? So if phi1 looked like some bump dx, and phi2 looked like bump dy dz, then if you were to take the integral of phi1, phi2, then because it's like these are in sort of orthogonal directions, if you could arrange it that way, then this should be equal to the integral of phi1 times the integral of phi 2. And this is just in the x direction, this is in the y and z direction, and that would give you 1. Does that make sense? So that's like an idea. I mean, I guess this lecture is going to be fairly hand-wavy, but I sort of want to show, I guess, how cohomology can be used for something. So yeah, I mean, a lot of the things I'll say today, I guess I'll state without proof. But hopefully it should be believable.
So on
That's
vibes, you
our
need
thing.
transversality because then your two forms at the points of intersection are going to be like not degenerate, and so you can actually integrate
Yeah.
and get a non-zero value.
So let's see what happens if you have like something where you don't have transversality. But yeah, that's exactly the point. So if you don't have transversality, what will happen is you have something like this. Now this bump form corresponding to the first one will be in these directions, right? And the second one will be in these directions. Now if you take the bump form at this point of intersection, they have this direction in common. And what happens then is that you end up with 0 because like dx equals 0, for example. So yeah, the transversality condition is to ensure that if you take the product of these two things, it'll integrate to 1 like you expect. Yeah. Does this make sense so far?
Yeah, I guess why isn't it that like if you had two things that weren't exactly orthogonal, that the sort of one magnitude perpendicular to one of them and the one magnitude perpendicular to the other one wouldn't get damped by the angle between the two of them?
This is a fairly good question. Yeah, I won't think on the spot about that, but I think if you, I mean, okay, well, you'd probably have something like, say like, okay, I'll just write B for bump, right? So you could probably have something like bump dx times bump, say, dx plus dy. And it's like, oh, the dx terms cancel out, but then this still has a bump dy. So, I mean, maybe if you like work it out a little bit more carefully, you can convince yourself that this should be true. Yeah. So our goal is to construct these Thom classes. How do we go about doing that, and what is the actual goal? Okay. So I'll give a definition of a Thom class, quote unquote. Definition of Thom class. So it's going to be a differential form, or I guess we should say, given some submanifold of codimension K. We're going to want to construct this is at the top.
Do these buttons do anything? Oh, it's running away.
Where is it?
Oh, of course.
Okay. Given something of codimension K, we want to, I guess I use a superscript for codimension, usually it's used for dimension, but whatever. We want to construct a form omega of, what's it called? Degree K, concentrated near S, bump normal to S, integrates, okay, the integral of omega in the normal direction And this makes sense because you have something which is the S is codimension k and omega is a k form, so this makes sense.
So like, is this like the integral of omega wedge normal direction, basically?
It's integral of omega. So if this is your S, then what you do is like you take a plane orthogonal to omega. A plane orthogonal to S, and integrate omega on this plane. So the integral so maybe I should say normal direction plane or something, is equal to 1. And we're going to further want a condition that d omega is equal to 0. Why do we want this condition? Well, first we were talking about cohomology, so if I somehow stop talking about cohomology, that would be doomed. But also, we sort of discussed this idea that I'll show you that this I'll state that this won't be true in general, but for closed manifolds this will be true. And the reason this should be true is because remember that one way that we can compute, so let's say again that this is your manifold S, and one way that we can compute the intersection of S intersect T is to take the integral over T of this omega associated to S, right? So if this is your manifold T, then we can take the integral of this guy that's perpendicular to S along T, and this will give us some number which counts the number of intersections. Now, if you remember, we said that this shouldn't change if we sort of move T along to another guy T prime. So what that means is that this should be the integral of T prime of omega S. And if you remember, then that this is sort of like saying that it doesn't change your deformation. And this, as we discussed a few lectures ago, is sort of equivalent to d omega is equal to 0.
In this case, it would be equivalent to d omega, like wedge the normal vector is equal to 0, right? Because what you're really doing is...
No, you're integrating it over T.
Oh,
Yeah.
I see.
So you're saying that it doesn't matter if you perturb T to some other guy. So then I consider it as a K form where you're integrating over K dimensional manifolds T, d omega is equal to 0. Right. So I guess this is like something that we're hoping for. I'll show that you can construct a form like this. But if your manifold is closed. If your manifold is not closed, you have something a bit interesting happen, which is that, say...
Is omega defined on a neighborhood of S?
Omega will
be
defined on the whole space, but it will be supported in a
so you can use partition of unity to extend it from a neighborhood of S, basically.
Yeah, that's essentially what we're going to do. Okay, so first, before I do that, let me state something, which I won't prove because I frankly don't know proof, but it should be believable. And state a consequence, which is a bit interesting. So say you have something like this. Say that this is your manifold S. Okay. So then I claim that d omega S is non-zero. What ends up happening is that, very nicely, d omega S is actually equal to omega, anyone want to take a guess?
Sorry, what is omega S? Is the
Omega S is the Thom class associated to S. Anyone want to take a guess as to if S has a boundary, what is the differential going to be equal to?
Omega of the boundary.
Yeah. So it's going to be equal to the Thom class of the boundary, which is cool, right? Because it's like D is some algebraic operation which raises the degree by 1. The boundary is some geometric operation which decreases the dimension by 1, so it increases the codimension. And so again, we get these codimension counts agree again. So what's the sort of, I won't give you a proof, but what's the sort of idea of this? Let's say that you have some part of a submanifold T over here. And we said that like the integral over T of omega S counts the number of points of intersection between T and S, right? So what happens if we deform this guy past the boundary to t prime? Well, over here you have a point of intersection, and then you keep having this point of intersection until you hit this boundary, and then the point of intersection is gone. So what that means is that this is not equal to the integral over t prime of omega s, which is equal to the number of points of intersection of t prime intersect s, right? So this is equal to 1, and this is equal to 0. And so what's the issue here? The issue is that once you pass the boundary, right, before you pass the boundary, you're still going to have this intersection point. But once you pass the boundary, the intersection point disappears. So one way that we can measure this is we can sort of fill in this deformation with a disk or somehow. And let's call this space maybe D. And we know that the difference, t omega s minus the integral over t prime of omega s is equal to the integral over d of d omega s, right? This just falls from Stokes' theorem again. However, the only way that you can lose a point of intersection is if you cross this boundary. So then that sort of makes sense to imply that this should be the integral over d of omega of partial s. And so what happens is if your s looks like this and omega s looks like this, then omega of the boundary is going to pick up this sort of perpendicular direction as well. And so that's what increases degree by 1.
Can we use this as an intuition for differentials in general? It feels like a sort of, because anything locally, vaguely speaking, is picking up some normal direction to some manifold, right?
The intuition for the exterior derivative, I think, is what I said in the first lecture, which is that it's whatever makes Stokes' theorem work. So, in a sense, yes. But yeah, I think like if you again run through the derivation of what we did, the exterior derivative, then it's a similar sort of a thing, right? You sort of looked at all possible normal directions that you can sort of extend your k-1 dimensional thing into a k-dimensional thing in, and then you picked up contributions for each of those, and that's how we like sort of got the formula for the exterior derivative. So in a sense, so this formula is kind of interesting because it has interesting consequences. Let's say that you have something like this, and you consider S to be these 3 circles on a genus 2 surface. So the thing is, this guy now bounds this surface, right? So if this is S, then S is equal to the boundary of some S prime. And so what that means is that if you take anything else and you try, let's say this is T, and you try and compute the number of points of intersection of T intersect S, right? Well, this is going to be equal to the integral over T of omega sub S. But then because of this, it's equal to the integral over T of omega d omega of S prime, because S is the boundary of S prime. But then this is a closed integral over a closed surface, so this is going to be equal to 0.
Wait, didn't you say that we always wanted to ensure that d omega s was 0?
Yeah, so while I was saying that, I said this is not going to always be true. It's going to be true if you have a closed manifold.
Have we proven that yet?
No, I'm going to prove that you can find one in a bit.
But that will imply that for any closed manifold, any intersection of 2 closed manifolds, the
Number won't change if you deform them. Yeah, I don't think I'll prove that you can find a thing like this. Maybe not exactly these conditions, but at least this guy And then
But this is stronger. This is saying you're closed, and if you're closed,
this is saying that
you're
if
exact.
this one's saying that if you are the boundary of something else, then this is exact.
So for an exact form, then your number of intersections with a closed manifold is 0.
Yeah. So this is interesting because like this says the geometric thing that if you have a submanifold, which is the boundary of another manifold, then that must have intersection number 0 with everything. Which over here you can kind of see because you can sort of start off at this intersection point and follow it until you have to leave at this intersection point. And you start at this one, follow it until you have to leave at this one. So it's sort of interesting that distinguish might be a sort of hard combinatorial argument that you have to be careful about. You can prove using differential forms in this way. Okay. So let's now give a sketch of the construction of the Thom class. Sketch of construction. Actually, do I want to give application first or construction first? What would you like to see?
Application.
Okay, so let's do the application. So let's put this off. Application, Bezout's theorem. So what does Bezout's theorem say? It roughly says that if you're in R2, or okay, let's start off in R2, and let's say that you have a degree K thing and a degree D and a degree E polynomial, then they'll intersect at DE many points. So over here we have like a ellipse, which is degree 2 polynomial, and a cubic polynomial, and they intersect at 6 points. And this picture was sort of suggestive in that you can almost see that these are like 3 vertical lines and 2 horizontal lines. Everything being black is not helpful. This guy becomes 3 vertical lines if you sort of like pull this guy up here and down here. And this one becomes 2 horizontal lines if you pull this one to the right and this one to the left, right? And the equations defining like 3 vertical lines and 2 horizontal lines are still a degree 3 and degree 2 polynomial. And so you count the number of intersections, and this is now a linear algebra problem, not even linear algebra, I mean. And you usually conclude that in this case it's DA many points. So it's essentially an intersection theory problem where you count how many, you can sort of deform your picture into a picture which looks nice, and then you count how many intersections you have in the nice picture, and then hoping that you have an invariance implies that you have your original count. So
You need both your curves to be closed for this argument to work, though, right?
yes. So what happens is, for example, like this guy is non-compact. This one is compact, but this one's non-compact. So there's 2 possible issues. The first issue, an issue is actually that if we're working in R2, then this already fails because R2 is non-compact. And I guess something which I didn't say is that this intersection form, because of this property, the intersection form actually descends down to an intersection on cohomology classes or homology classes. So you have a pairing from h n minus k times h n minus l to h n minus k plus l. So remember that this is homology. So this is saying that if you have a codimension k and a codimension l manifold, you can take their intersection and get a k plus l manifold. And this is expressed in cohomology language as saying that you have something like this. Now, we're going to apply this in this case, but what happens is R2 is pretty bad because it's not compact, so you can actually all the cohomologies are 0, so all the Thom classes are 0, and actually you can remove all intersections. So if we can like deform these in arbitrary ways, what we can actually do is like sort of deform this whole circle to the left and remove all intersections and get a picture like that, right? And that is not what we want. So what can possibly happen if we deform our picture? One thing that can happen is if we have two lines which intersect, for example, we discussed this a little bit a few lectures ago, then we can sort of deform this line by rotating it until it becomes parallel. And then the point of intersection sort of runs off into infinity, right? A second issue that we can have is, let's say we have a circle and we have a line, and we sort of move the line to the side. That's 2 points of intersection, 2 points of intersection until you get to no point of intersection. And what happens is, at this point, it becomes tangent. And so, you know, high school competition geometry will tell you that you have to compute some sort of a discriminant here. And if the discriminant is greater than 0, then you end up with this case where you have two real points of intersection. If the discriminant is equal to 0, you get a tangent point. And if the discriminant is less than 0, then you get no points of intersection. But over here, you still do have like 2 points of intersection. It's just that they're complex intersection points. Does this make sense?
Yeah.
Okay.
Wait, but I guess I don't understand, like, what's happening in projective space? Like, if you try to deform your curves in this way, why is that being prevented in projective space? In this one? In that picture?
This one?
No, the other picture.
This one?
No, with the two curves.
This
When
one?
they used to have D times E intersections.
Oh, this is...
They all at the point of the...
No, this one is not the projective picture. This one is the real picture. Here, the intersection still exists.
In
They're
complex?
in the complex.
So but in the complex case, that's still contractible. So what happens in the
It's not contractible. CP2 is not contractible.
Right. So before you make it projective, imagine you were to separate the two curves fully.
Yeah.
Or is that not possible?
It is possible.
So if
because
you
it's
separate them
contractible.
fully, what does that mean? Does that mean that all of the intersections are happening at the line of infinity?
Yeah. Yeah, I mean, like that's what happens over here, right? For example, if you like make the two lines parallel.
Right.
Okay, so what is this? It's going to be the space that we talked about a few weeks back, CP2, and we computed the cohomology of CP2 in one of our problem sessions, and we saw that this was R0 R0 R. So if we cut out an equation by a polynomial, then that corresponds to a two-dimensional real submanifold. So we should be looking at Thom classes in H2. And if we take the product of two of those guys, then we get something in H4. Yeah. So
we should think of Thom classes as constructive ways of getting the cohomology class, like the associated to a submanifold by Poincare duality or something.
Or something. I haven't talked about Poincare duality yet, but kind of. I mean, yeah, you should consider it as, well, yes, actually. That's basically the idea. That it's an explicit way of sort of talking about this intersection pairing using cohomology. So what can we do with this? Well, let's consider a hyperplane. So equation z equals 0, for example. And let's say that this has some Thom class, which I'll call omega sub h, right? And if we look at what is this product? So omega sub h dot omega sub h. And what do I mean by that? I mean that this is equal to the integral over CP2 of omega sub h wedge, omega sub h prime, let's say. Actually, you can also take omega sub h. So there's an interesting thing. I think you can take omega sub h. There's an interesting thing where if you Yeah, if you take a one form dx, wedge dx, this is always going to equal to 0, right? But you can actually find examples of forms where omega wedge omega is not equal to 0. For example, if you take dx dy plus dw dz, and you wedge this with itself, then what you're going to get is something like 2 dx dy dw dz. That's pretty interesting. What would you do if you...
When they're even or something?
Yeah, if they're even, or in other cases as well, you can find some examples. I think this should probably be fine, but if necessary, then you might have to perturb the hyperplane a little bit. And this integral should come out to be 1, right? Because we can do just linear algebra and show that if you have two hyperplanes in real projective space, which we can think of, for example, as the intersection of two hyperplanes in C3, then we know those must intersect at one line, which corresponds to 1 point in CP2. So this integral should be that. Okay, so let's say that we have that's an awful submanifold. Let's say that we have some submanifold S. Okay, and this corresponds to a degree D equation. So then what you get is that, what does it mean to be degree D, by the way? Degree D means that you have some f of xy such that the highest degree is equal to D. So let's say that we take the intersection of S intersect x equals y, right? Well, what is this going to be equal to? This is just going to be the solutions to a degree D polynomial equals 0 in x. And so what is the number of points of this? Well, it's equal to D, right? So we can realize the degree geometrically as being the intersection of the surface with a generic hyperplane, right? And So what this means is that if you look at the Thom class of S here, of SD, then this is gonna, if you pair this with omega h, the hyperplane, this can be equal to D, right? But the cool thing is that we know that H2 is one-dimensional. So what that means is that this is actually some multiple of this guy. And we know that if you take omega h dot omega h, you're going to get 1. So that tells you is that omega SD is actually equal to D omega h. And now we conclude by saying that if we have omega SD times some other surface, then we're going to get D times E of omega h squared, and this is equal to DE. So now
We know that taking the integral of omega h is
integral of omega h squared is 1.
right.
Yeah. Now there's one caveat to this, which is to say that
Should this have integrals in front of each of the three things, or
I guess there should be
or
an integral of this is equal to DE.
I see.
Yeah. So there's one thing that you have to be careful of, which is remember in the real case, what we can do is we can sort of perturb this to something like this, and now we have more than the number of intersections. But the thing is, we have orientations involved, right? So we have a plus, minus, plus orientation. So the cool thing is, because we're working the complex numbers, if you have a solution, okay, so let's say that we're looking in some sort of a C2.
Oh, so you're saying that in the real case, orientations lie to you?
No. I'm going to show you why orientations don't come up here.
Okay.
So they're okay. So
But they would lie to you if you were looking at these two pictures, right? If you were doing this in RP2, this shows you that a cubic and a linear term aren't distinguished from the intersection theory perspective.
No, I'm saying that you can deform this line into this picture.
Right. So the real picture is lying to you, or
No.
Okay.
So why is it that like you could possibly have this case where you have two guys, say like two spheres which are both degree 2, but they intersect at 6 many points with like 5 positive orientation and 1 negative orientation, right? So why can this not happen? Certainly, you can actually deform the two spheres in a real sense in order to get this to happen, because you can just artificially create intersections, right? Just like how we did over here. But you can't do this while keeping them both polynomials. And so the reason is, like, if we work in C2 with coordinates like z omega, so this is inside CP2, then locally, any polynomial, so this is f of z w is equal to 0, locally this can be written as w is equal to g of z. So this is your w and z axes. And it's saying that locally around every point, you can either find that w is a graph of z or that z is a graph of w. Assuming it's not singular, I'll just take that for now. If it is singular, maybe you have to do some more work, but whatever. So what happens here is that this is some holomorphic coordinate, right? G is holomorphic. And so if you were to write the Thom class, the Thom class should be sort of perpendicular to this in some sense. And so it turns out that you can find a Thom class which is written exclusively in terms of dz. Sorry, I shouldn't say it. In terms of, let's see, let's say dz is equal to z1 plus I z2 and w is equal to w1 plus I w2, then you can write something in terms of dz1, dz2, like this, okay? And the fact that you have a complex structure means that you have like a prescribed orientation where you say, take the real part before the imaginary part. Similarly, for your other guy, you can write a form in terms of dw1, dw2. And so what happens here is if you take the product of them, if you always go with the convention that you take like dz1, dz2, dw1, dw2, then it doesn't matter in what order you multiply them. So in this case, it sort of mattered as to whether you took this one first or this one first, right? So in this case, if you take this one first and this one first, then you're going to get one orientation. If you take this one first and this one first, you can get the opposite orientation, right? So in this case, it doesn't matter, because even if you swap these two blocks around, you're still going to end up with a factor of -1 to the 4th, which is equal to 1. So because you have these like blocks of real and imaginary parts, you get that every point of intersection actually has to happen with positive orientation. So this is one of the special features of like including the fact that we have complex numbers into the fact, and then we can guarantee that all of our intersections have positive orientation. And so this actually gives us not only like intersection which is invariant, like some sort of flabby intersection which is like invariant under deformations, like we had in this picture. This gives us more rigid upper bound as to the number of intersections that we can have. So the theorem says that you have less than or equal to d many points of intersection. You can have less than it if it's tangent or you have some singularities or something like that.
So what would happen if you tried to replicate this intersection theory story, but you did it in RP2? What would you get as the intersection number of two?
You can only
polynomials?
count things mod 2.
Okay, that makes sense.
Yeah, so in RP2, what happens is de Rham cohomology just fails completely, and you end up getting zeros everywhere. Not everywhere, but in a lot of places. So what you actually have to do is look at integral cohomology and take Z mod 2 cohomology, and then that takes into account that you can count only the number of positive intersections minus the number of negative
And that's what we're
intersections.
seeing here.
Yeah.
We're saying because you pulled out two of the intersections.
In this picture, yes.
Right. Whereas in the complex case, precisely because it's oriented, which you're showing us by showing that you can canonically choose like a complex differential for your polynomials, you have non-trivial classes which happen to be represented by your polynomials of the given degree.
Sorry, repeat the last part.
That you get cohomology classes which happen to be represented, like non-trivial cohomology classes that are
Well, you're always
represented
going to
by
have
polynomials.
non-trivial cohomology classes. Just that in this case, the intersection is guaranteed to have positive orientation.
For polynomials.
Yes.
Because you can always get it to be D.
Or for complex submanifolds in general.
Got it. So whenever you have holomorphic stuff, as
Yeah.
opposed to.
As opposed to like real, yeah, as opposed to like some general real manifold. Yeah.
Wow. So polynomials, you never have fake intersections that cancel each other out. You
Yes.
always genuinely have DE intersections.
Yes. Yeah. Or less than or equal to, because you can have like
Degeneracies.
degeneracies, but
That's
or like tangencies, but yes. Yeah. So I guess one other thing is like, maybe I just want to quickly mention, because I always hated this concept of orientation. Like the definition always just seems so weird. It's like, okay, you want to choose a canonical like choice of basis at every point, and it's just sort of a strange definition. So, but I think this intersection theory picture like kind of tells you why you want that to happen, because like if you want to be able to count things with signs properly, right? We saw that things can like cancel each other out, so you need to be able to choose like a choice of frame properly. And I guess one of the things that's confusing about orientation is like it's something which seems like it should obviously be true, because locally it is always true. You can always locally find orientation. So orientation is actually more of a global concept. And so like, you know, we've all seen the Mobius band. How do you draw a Mobius band? Something like this. And so what happens is like if you have, say like this curve and this curve which intersect like this, and sort of like move this intersection all the way around the circle, what'll happen is like the frame itself has switched. So you don't know whether to count this as a positive or a negative orientation. And so this corresponds to the fact that in order to count the number of points of intersection, right, we've been taking the integral of the product omega 1 wedge omega 2 over a whole manifold M. But this relies on the fact that the manifold M is actually orientable. If M is not orientable, turns out this integral will always end up being 0, I think. So cohomology-wise, we can define an orientation to be a non-vanishing top form. And so why does this give you an orientation? Because remember, like we said, like if you have some differential form, then you plug in vectors E1 through En, and you can tell what the orientation is, whether this is greater than or less than or 0. And saying that this is non-vanishing everywhere says that essentially that this sign cannot ever change. Now this is equivalent to, well, no, sorry, maybe not equivalent to, but this implies that the integral over M of this orientation form omega is non-zero. And so you can define an orientation to also be a generator of Hn of M, where this is the dimension. I should say non-vanishing, I guess. Yeah, so you can take it to be a non-vanishing top form, and that's a definition of an orientation. And so when you want to...
It's closed, but...
Yeah, because it's closed.
And
And
it's not exact. Okay, I see.
or I guess I should maybe say not defined as again, but I guess an orientation gives you a generator of the top dimensional cohomology. And this is a useful statement in some regards. Yeah. So...
Can I ask a question?
Yes.
So, intersection theory in like algebraic geometry, I've always thought of it as like kind of like butting heads with topological intersection theory. But this is giving me the feeling that like as long as you work in like complex manifolds, actually topological intersection theory does the same thing as algebraic intersection theory. It's just algebraic intersection theory focuses on polynomial surfaces. Is that right?
This is correct. It's also really interesting because you can show that if you take any complex submanifold, any holomorphic submanifold of CPN,
It's an
which is
algebraic
compact,
variety, right?
it's forced to be a solution of polynomials. So in that sense, like these two statements are equivalent. It's like
Up
in
to complex isomorphism or literally?
literally. So in algebraic geometry, when you take intersections, you're sort of working with this algebraic machinery. But you can, as long as like you know that you're working inside CPN, you can transfer this into sort of a differentiable statement using this topological theorem cohomology. And a lot of things that you can do in algebraic geometry you can sort of like translate over into sort of a differentiable setting where you can like do some interesting things. Because you can do like, you can't look locally in algebraic geometry, but you can look locally in cohomology and topology, which allows you to do some useful things. And Hodge theory initially started off as something to understand complex submanifolds, and people found it so useful in algebraic geometry that they decided to try and generalize as much as they could to like more pure algebraic geometry settings. So more so, you can also like sort of leave this strict thing of like complex varieties and talk about some complex manifolds, or if you want a bit more structure, something called a Kähler manifold, and use a lot of tricks from
So what does that do?
complex
What does this
geometry
symplectic
into a
extract
Kähler. We won't talk about that right now.
Okay.
But you can transfer a lot of things from algebraic geometry into, or ideas into some more general topology sort of thing, and see how it plays. Yeah. So one interesting interpretation that I wanted to mention on this. So we saw using Meyer v. Torres that this H2 of CP2, right, comes from, quote unquote, the H2 of CP1. Right? We saw that we had like a C2 with the CP1 at infinity, and this H2 essentially like comes from this guy. So that means it's like you have some sort of a spherical hole inside CP2. And interestingly, what our discussion so far has told us is that a degree D surface sort of actually wraps around this guy D many times. So there's a copy of CP1, which is non-contractible, and from the fact that omega SD is equal to D of omega H, you have this interesting picture that like the degree D surface like wraps around the sphere D many times, and this is sort of analogous to like how on the torus, if you have this circle and this circle, then they have zero intersection because this guy's contractible. But if you have this circle and this circle sort of wraps around twice, then like the intersection is measured by how many times each individual circle wraps around the two holes of the torus. So this is sort of analogous thing where you have one hole here, and you're measuring how many times does this wrap around the centrosphere. Yeah. So maybe since we started a bit late, I'll go a little bit over, but I won't go into a lot of detail of the proof of the existence of this. You can read up more about Button too. It's in the first chapter. Everything's in the first chapter. Honestly, read the first chapter and like you'll know basically everything you need to know from a practical point of view. Okay, so sketch of construction. So as was previously mentioned, what we're going to want to do is take a submanifold, and we're going to restrict ourselves to a little neighborhood of the submanifold. And what this neighborhood is going to look like is going to be a bunch, we can like think of this as a bunch of copies of R to the D, where we're codimension D, which are all perpendicular to our submanifold S. And what we're going to do is we're going to construct a bump form, which is going to integrate to 1 on each of these fibers. Yeah, so I mean, we can restrict to, we can sort of translate our problem into this problem of like, you have your submanifold S, and you have some planes perpendicular to this, and in each of these planes, you just want to find something which integrates to 1 on each fiber. And then using some homeomorphism, you can like shrink this whole plane down into like an arbitrarily small circle around S, right? And it's not around S. Maybe I should draw the picture around S. And so then you can sort of transfer this bump form into your submanifold, and you have a bump form which is concentrated around S. And what this proof will show is like, assuming you believe that tubular neighborhood exists, which is arbitrarily small, that you can actually find a Thom class representative which is arbitrarily close to S. I guess one other thing which I hadn't stated until yet is, let's say that you like take a point and you find some Thom clusters concentrated around here, and you take another point, you take a Thom cluster concentrated around here. These are different differential forms on a literal level, but once you, so like let's say this is omega 1, this is omega 2, then omega 1 is clearly not equal to omega 2 because they have different supports. But turns out if you look at their cohomology class, their cohomology classes will end up being the same.
Why would we care about wanting the Thom class to be supported as close to this?
For example, a transversality issue. If you have something like this, right? So if your Thom class was like this big, you would have issues here where like, we said like over here you can kind of decompose the integral into like this part and this part. But if your Thom class is kind of large, then it'll be difficult to do that. So instead, you want to be able to guarantee that you can make your Thom class concentrate really close to your guy. So that transversality means that like locally it looks like linear algebra. And so what we want to say is that we can make our Thom class small enough so that we can use that approximation. Yeah. Okay, so first off, let's do this construction for if we just have S cross R to the power of D. So what do we do here? Well, we saw that if we have a sphere of dimension D minus 1, then we have the volume form of the sphere, right? We saw how to construct this. This is like is equal to the volume form of R to the n with the normal vector first, and then the rest of the vectors as inputs. And so we can construct this volume form of the D minus 1 sphere. And then we can wedge this with D of some function, which let's say looks like this. So D of this phi here, and so this will be -1, 0. And so the point is that if we call this guy omega, then the integral of omega is going to be the integral of the volume form of the D minus 1 sphere times the integral of d phi. But then because this goes to 0 infinity and -1 here, this will just be 1, and this will just be some constant, which I'll just call CD, the volume of the d-dimensional sphere. So maybe we should do this as volume to c-dimensional sphere divided by CD. So this will be 1 over CD, and so this will be 1. And so we get that this integral is equal to 1. And also the support of omega is just going to be inside that little region where d phi is non-zero, but also like radially supported because of this volume form. So this sort of achieves our goal in the case that we just have S cross R to the D. We just take a copy of each of these omega forms on each fiber, and we have this guy. And so because the volume form is closed and D is closed, we can see that, okay, so if we were to compute d omega, right? Maybe this will be a good time to state this. If you have two forms, alpha and beta of degree k and L, then d of alpha wedge beta is going to be d alpha wedge beta, d alpha wedge d beta. But you get a sign over here, which is -1 to the power of L. And so the point is that this comes from the fact that you sort of have to move D, which is like a degree 1 object because it increases the index by 1. Sorry, this should be -1 to the power of K. Across these K guys. So you can do the explicit computation and check that this is true. This is generally called something like the causal sign rule. It's sort of related to the fact that alpha wedge beta is equal to -1 to the power of K L beta wedge alpha. So you should think about the fact that like when you swap the alpha and D, you have to pick up a factor of K because this is sort of degree 1 and this is degree K. So if you compute this, then d omega is equal to d of the volume form as d minus 1 wedge d phi plus volume wedge d squared phi. This is always equal to 0. This is also equal to 0. We showed yeah, if you take the thing which is constantly this, then it should be equal to 0. Or I guess actually no, this is like a dumb statement, right? Because this is a D form in RD, so yeah, it's gonna be equal to 0. So d omega is 0 on RD, but is, I guess, let's say big omega is equal to copies of little omega on each fiber of S cross R to the D. So you have S, you have a bunch of these guys, and each of these you put a little copy of omega. Is d omega equal to 0? Because we wanted that so that it'd be closed. And you can sort of show that this is true for a stupid reason, which is like in local coordinates, omega is constant in the S directions. So if you sort of move this way, then I mean all you're seeing in any direction is little omega, so it doesn't change any of those directions. So d omega is equal to 0 in those directions. We show that d omega is 0 in the vertical directions as well, and so d omega is equal to 0 in all directions. So that's cool, but this doesn't quite complete our proof because this only covers this case, and the point is that your neighborhood of S will always have something which has like a fiber of R to the D. And hopefully we'll get a chance to talk about vector bundles later, but I don't want to get too deep into it right now. All I'll say right now is something which projects onto a smaller manifold where each fiber is RD is not necessarily the product. So we've already seen an example of this because if we look at CP1 inside CP2, which is just a hyperplane, then we know that the normal, it's called the normal bundle, but the tubular neighborhood cannot be R2 cross CP1. Because if it was, what you can do is you can take a copy, okay, so let's say that this is CP1, and let's say this is R2. You can take a copy of another copy of CP1, which like is like CP1 comma the point 0 comma 1, right? And these two guys don't intersect each other at all. So you can sort of deform CP1 off of itself in the normal bundle or in the tubular neighborhood. But we saw that if you deform CP1 off of itself, it has to intersect itself regardless. So what that means is that this whole thing cannot be this. Does that make sense? So what's the general proof strategy? Well, what happens is what you can do is sort of modify your definition of cohomology for a bit. So if you have, I'll give an informal definition of a vector bundle. So vector bundle E over S of rank D is a projection of manifolds such that each fiber, so each preimage of every point is R2 to the D. And what I want you to think about, there's two cases in particular which are important, which are normal bundles, which are essentially small neighborhoods of your point, so tubular neighborhood, and tangent bundles. Hopefully near the end of the class, we'll be able to talk a little bit about vector bundles and stuff about those. So this is sort of just giving some introduction and some examples of these. And each time you have like non-trivial self-intersection in a manifold, that gives you an example of a non-trivial normal bundle. I'll maybe state a quick thing at the end about that. So what you can do when you have such a situation is consider something called cohomology with vertical supports, compact vertical supports. So I'll denote this as HCV of E. And what this is same thing, except you can only consider differential forms, which go to 0 as you go to infinity in the fibers. So this is essentially what we were doing with the tubular neighborhood. We want something which like goes to 0 away from it, and that way you can sort of like put this thing inside of a manifold if the vector bundle represents a tubular neighborhood of something. And we can extend it to 0 outside, right? So what we've shown here is that compactly supported cohomology, cohomology with compact vertical supports of S cross R to the n, or you can show that this is equal to H, the normal cohomology of S. Let's say that this is in degree K. Should not use n here. Say D. In dimensions D minus K. And so how do you do this? Well,
T minus K or K minus C?
K minus C, sorry. So what you do is you have your fibers, and so you have a map from this guy going to this guy, which is integrate on fibers, right? And that'll give you some differential form over here, and you have reduced the degree by D because you've integrated away D things. And then you have a map over here, which is multiply by omega, which is that form that we just constructed, which has integral of 1. So these two aren't exactly inverses of each other because, you know, if you have something which is concentrated far away, for example, over here, then if you integrate that and then you put it back, it won't be exactly the same thing. But you can show that if we call this F and G, that G composed with F star. So well, okay, so if you go this way, right, then this is literally the identity, because if you multiply by omega, then that integrates to 1. So F composed with G star is equal to 1 already. This is equal to, not equal to 1 on forms, but again, you have this sort of a trick where you have something called a homotopy operator, where if you take this minus 1, this is equal to something, which you can check the book, plus or minus dk, and this is some operator on differential forms, and this shows that G composed with F star is equal to 1 on cohomology. So what that amounts to saying is that if you compose these two maps in either direction, you're going to get the identity map on cohomology, and so these two maps form an isomorphism between these two spaces. Okay, so how do we finish our proof now?
You need it to be on compact support. Didn't we say at some point that when you...
Compact vertical support.
Didn't we say at some point that when you take a cross with a real Euclidean space, it doesn't change cohomology?
Yes, but this is different. This is compact vertical support. It's these are forms which go away as you go.
But in this case, they're isomorphic. Like if we replace the compact vertical support with normal, it would still hold.
Yes, except you don't have a degree shift. That's for a different reason.
Oh, okay, I see.
Yeah, so in this case, you have a degree shift. And one way to think about compact vertical supports is like you're trying to take this tubular neighborhood and put it inside a different manifold.
Right.
And so if you had these isomorphisms with the cohomology of S itself, then that would mean that like if you embed S into any other manifold, sort of the properties of S with respect to the ambient manifold wouldn't actually care about the ambient manifold, which is obviously not true. We've seen examples now that that isn't true. So now how do you finish the proof? What you say is you take S and you break it up into small charts, such that over each fiber you do have UI cross R to D. So you have E, but then E restricted to UI, so the preimage of UI is equal to this. And then what you can do is essentially Meyer-Vietoris argument, a similar sort of thing where you patch things together, and you use this isomorphism over here to patch parts together from, say, UI intersect UJ. You have a map from this going to UI union UJ. You have a map from this going to the sum, and then again the intersection, and over here again the sum. Okay, so here this is the sum of UI and UJ, right? So what can we consider? We consider the cohomology with compact vertical support. We consider the cohomology dropping the degree of the base space, right? And we know that so we have a similar thing over here. We have sum, intersection, union, sum, intersection. And we know that this forms an isomorphism on the basic UI parts. And we sort of build it up inductively by saying, okay, this is an isomorphism, this is an isomorphism, this is an isomorphism, this is an isomorphism. And so by the 5 lemma, it turns out that this is also an isomorphism. 5 lemma is something which says, like, if you have 4 of 5 isomorphisms over here, the middle thing is also an isomorphism. And so from that, you sort of like patch things together from, say, this set plus this set to their union, then you include this guy, and then you include this guy, and then you build it up step by step until you get that on the full manifold, H star CV is isomorphic to H star minus D of S. And so the Thom class is defined to be, so let's call this map phi. This is defined to be phi inverse of 1. So this will have a degree D, as was expected. And the reason that we take phi inverse of 1 is that, again, you can check the book since we're running a bit low on time, But this will essentially say that integral is equal to 1 on fibers. And so this was an indirect sort of construction where we sort of glue things together using Miravita torus. There's sort of an explicit way that you can describe this using an angular form. This is covered in chapter 2 of blocking 2. But if you do that, you can sort of show that this will look like a bump form in the perpendicular directions.